This is our first video lecture in the module on Bayesian modeling and analysis. And with a good background now in probability and in priors, we're almost ready to start seeing how we can use Bayesian modeling to approach some interesting problems. But we need a couple additional concepts, and these come from statistical decision theory, and that's the discussion in this video lecture. Specifically, we'll look at the concept of Bayes optimality for two problem sets, quantitative response and qualitative response. So let's start with quantitative response. And we can set the problem up by letting y be a quantitative output and x be the input, where x is, again, a matrix. Y could be something like, for example, the score that a patient receives on a test for their triglycerides. And X could be a series of measurements that we have that include the body mass index of the patient, the blood pressure of the patient, and other scores that we have on that patient. And in this case, the response, the measurement of triglyceride, is considered a continuous value, so we consider part of the real line. And each one of the predictor variables, the X's, we consider to be part of the real line as well. So they, in fact, form a subset from P, let's say P-dimensional space. It could be 3 dimensions, it could be as many as thousands or even millions of dimensions that we're using in order to make the prediction of that quantitative response. We'll let capital P, X, Y be the joint distribution of these first random vectors and then the random variable y. Our goal is to find a function, then we'll call it y hat, which is a function of these predictor variables for predicting what this new value for y, or it may not be a new value, but predicting or estimating the value for y for, let's say, a particular patient. And that's what we're interested in. We score our prediction using a loss function. So this L then is the loss function, the y is the true value, and the f of x is our estimated value for y. So we look at some scoring function that basically tells us how well we're doing in our prediction f of x of y. We define Bayes risk then to be the minimum, and it's shown here as INF, or infimum, of the expected loss. The expected value for the loss function when we integrate or sum it over all possible values for x and y. And this gives us the score then, and we can look at the smallest of these scores. Now, the reason we use infimum as opposed to minimum is because technically, mathematically, it's possible that we may not be able to actually achieve the minimum, and this just tells us we're getting the greatest lower bound on this function. But for all practical purposes for us, we want to minimize this, and that means that the Bayes risk is the one that minimizes it if it is in fact possible to minimize it. And that function then that does do the minimization is what we call Bayes optimal. Again, if it exists, this is the Bayes optimal solution. And this Bayes optimal solution then gives us the Bayes risk, the minimum value that we can obtain on the expected loss. Let's look at a particularly popular loss function, which is the squared error loss. And this is one that we will use. It's not the only one, but it's definitely the most popular of loss functions. So it looks at the value, the true value y, the predicted value f of x, and it looks at the difference between them and then squares that difference. So we can talk about the expected square prediction error and define that very simply as the expected value of the squared error loss. Or more formally, we will integrate over all values of x and y the score function, this squared difference between the actual value and the predicted value. And we can also write this, we mentioned this before, using these expectation operators. the internal expectation operator is the expected value, and it's taken in terms of the conditional probability of y given x. So this is a conditioning argument. And then the outer expectation then removes the values of x, so it conditions over those values. And that gives us then the expected square prediction error. The Bayes optimal predictor is given by this conditional mean. So it's given by looking for the value that in fact minimizes that expected square prediction error. And it's easy to show that for squared error loss, that Bayes optimal predictor is the conditional mean value. So this, in fact, can be considered to be the universal machine learning solution. And this is really what we're after in many cases, is just finding a way to estimate the conditional mean value. Okay, so that's the answer for quantitative response. Let's look at what it is for a qualitative response. In the qualitative case, we have a categorical response, and we're representing that here with G, which is a capital G, which is a subset of the script G set. And for example, we've given many times the admission to UVA. Our script G then would be don't admit, waitlist, or admit. And the G value would be, the capital G would be one of those choices. So our decision function then would actually, again, select from these the actual value. So to make it clear to you, the capital G is the random variable. So that's what we draw for that particular observation. When a student applies, that's the random variable associated with that student. The D of X, on the other hand, is our decision, what we actually decide to do for that particular student. With, again, in this case, the X again represents values that we have about that student. So they could be the GPA, they could be scores on GRE tests, they could be the number of clubs the student has been involved with, they could be scores that people have given on the letters of recommendation. All of these could be inputs to this process. So again, we need a loss function. And this loss function then is going to measure the difference between the true value of the categorical response, and that's little g sub I for that particular student, and the decision that we made for that student given their scores on all those predictor variables. And this is our way of deciding how we're going to classify any given observation. A common choice for this particular problem for a loss function is what's called 0-1 loss. And it's a very simple and intuitive loss function. It basically says that if the true value is for this particular individual or this particular observation is equal to what we choose it to be, then we get a zero loss. We're basically rewarded by having no loss. On the other hand, if we get it wrong, if we pick the wrong answer, then we have a value of 1. So the loss then is 1 if we incorrectly select, and it's 0 if we correctly select. Okay, the expected prediction error then, given that, we can write as the expectation of this loss, just as we had in the continuous case. And the expectation, again, is over the joint distribution, in this case, the joint distribution of G and X. But since it's a discrete case, we have a summation to describe it. And in particular, we can condition on the value of X in order to find this expected loss. And the minimum of this loss, of this expected prediction error, is again Bayes' risk. And for any particular value that we see in our predictor variables, the Bayes optimal decision rule then is going to be given by the value that of the decision, the decision that minimizes this expected loss. And that's what this says. This argmin just says, look, of the choices you can make within script G, again, you could think about that as wait list, deny, admit. Of those three choices, the one that minimizes your loss for that particular set of observations is the one that you should choose. So it's a very, again, intuitive thing. We're going to pick the one that minimizes our loss. And that's all that's saying, and that's the Bayes optimal decision rule. Now, it turns out that when the loss function is 0, 1, the Bayes optimal rule is particularly easy. It just says we're going to pick the most likely of all the possible outcomes. So if given, again, the set of performance values that we observe on this student, we're gonna pick either admit, deny, or wait list based upon the one that is the most likely. Which one is the most likely choice for this particular set of observations? So given their GPA, given their GRE scores, let's pick the response that's the most likely. And again, you can apply this to any problem. You could say, if I have to choose if this patient has the flu, if they have a cold, if they have allergies, given their measurements on their temperature measurements, their blood pressure measurements, and all the other things that we could take on them, given those things, I'm going to pick the one that's the most likely. And that's the Bayes optimal decision rule. Again, it's a very intuitive kind of rule that derives mathematically straight out of the notions of Bayes optimality. And this notion of breaking ties arbitrarily just says, look, if it turns out, because this is a discrete case, that let's say being waitlisted and being denied are equally likely, then you should flip a coin. At that point, it's just an arbitrary decision. So randomly choose, flip a coin, which one you're going to pick. Same thing with a diagnosis. Same thing in general. Always, if things come up as a tie between categories, break ties arbitrarily. Okay, with this foundation now, the rest of this module will look at methods that we have for constructing classification functions that are Bayes optimal under known distributions. We'll also estimate likelihoods and apply Bayes' rule to get our posterior for the choice of a category given the observations that we have.